Imagine asking a state-of-the-art AI system a simple question like, what is 2 plus 2? And in response, the system activates a massive, multi-step retrieval engine, spinning up servers to scour external databases just to spit out the number 4. It's like using a massive cargo ship to deliver a single envelope across town. For years, early retrieval augmented generation, or RAG, systems operated on a single, expensive assumption. They were built to treat every user prompt as if it required an external database search to find the answer. This flowchart illustrates what happens during a single search. The moment a user hits send, the query multiplies into a bloated pipeline of computational tasks. The system generates embeddings to convert text into numbers, queries vector databases, ranks incoming documents, injects that context into the prompt, and burns through extra tokens. Multiply that heavy sequence by millions of daily users inside a large enterprise. The sheer volume of processing power required causes server costs to spike and introduces noticeable latency into every response. Researchers looking at this problem eventually realized a counterintuitive truth about artificial intelligence. The smartest retrieval system isn't the one that searches the most, it's the one that knows exactly when to stop searching. Treating every query with the same weight forces a language model to wait on slow, expensive database calls it never actually needed. Consider two different requests. First, what is the capital of France? Second, summarize the last 6 months of internal engineering reports and identify recurring operational risks. Clearly, these are completely different tasks. The first can be answered directly from the model's pre-trained knowledge. To avoid wasting resources, the AI has to be trained to evaluate its own knowledge gaps before it takes any action. The system learns to run a triage evaluation based on specific triggers. A time-sensitive question, like what happened in the stock market this morning, or a private request asking for company compliance policies, tells the model that external data is strictly required. A generic factual question tells it to skip the search entirely. Accurately categorizing user intent up front is the absolute prerequisite for saving computational resources at scale. This diagram maps the adaptive RAG framework. Its core innovation is a new starting gatekeeper, the decision layer. For simple queries, it bypasses heavy vector databases, routing straight to the language model for immediate answers. Complex queries trigger the full resource-heavy retrieval pipeline. This simple architectural fork acts as a massive filter for the entire system. It intercepts and resolves the easy tasks instantly, long before they can consume expensive database resources. The decision layer functions as an intelligent router, ensuring computational power is spent only when the internal knowledge of the model reaches its limit. For large enterprises handling 10 million user requests a day, the math is highly favorable. If half those queries don't require retrieval, you eliminate 5 million unnecessary database searches every day. Infrastructure costs drop, response times shrink, and heavy compute power is strictly reserved for the complex analytical tasks that actually need it. Adaptive RAG solves the efficiency problem of when to search, but it exposes a deeper flaw in how search is performed when complex queries get through. Traditional retrieval has an inherent weakness. Systems slice complex documents into dozens of isolated, disconnected text chunks. It's like cutting a book into random paragraphs. Once fractured, the vital relationships and causal links are completely destroyed. If you ask the system which customers are connected to suppliers affected by the recent regulatory change, the answer isn't sitting in a single paragraph. It is scattered across a network of relationships, a network that traditional chunk-based retrieval cannot easily reassemble. Answering complex enterprise questions requires a system capable of mapping relationships rather than simply indexing isolated fragments of text.